one of the simplest solutions for camber line design is what's called the uniform load. The uniform load is actually what was used for the NACA 1 series. So this is one of the early airfoil series developed by NACA. So we start here with our equation, our fundamental equation from thin airfoil theory. And what we're going to do is for a uniform load, basically we say that gamma is constant. So we want a constant strength or a constant delta in pressure across our entire airfoil, and that will give us what's called the uniform load lift distribution. So we're going to assume that gamma is constant, and we're going to solve for the camber line slope, which is dyc dx. Okay, so let's do that with this equation. I'm just going to jump to the solution here. What we'll get is that dyc dx is equal to alpha minus, now gamma is constant, so I'm going to move it outside of the integral. It's going to be gamma over 2 pi v infinity, that's a 2 there, times the integral of x naught from 0 to c of dx naught over x minus x naught. Okay, so that's what this whole equation simplifies down to if we make those assumptions and solve for the camber line slope. Now the integral, this integral that we're left with is a little bit tricky because it is singular when x equals x naught. And so in order to integrate that, we actually have to look at the limit of that solution as, say, an epsilon approaches 0, and we integrate from the left and from the right. So we'd integrate from x naught equals 0 up to x minus epsilon of that integral, and then we would add the integral from x naught equals x plus epsilon up to c of the integral. Okay, so we'd have to work through that. But what we get then when we do that is that this is equal to minus the natural log of c minus x over x. Okay, so we can solve that, but it is singular where x, when x is equal to x naught. Okay, so now we can just plug the solution in to our equation over here. We get alpha minus gamma over 2 pi v infinity. And actually this is going to be a plus now because we have a minus over here, and multiplied by the natural log of c minus x over x. All right, now the next step, what we want to do is put gamma in terms of our desired lift coefficient. So let's look at what gamma is in terms of lift. So we know that the lift is equal to rho v infinity times capital gamma, which is equal to rho v infinity. So this is a Kutta-Joukowski law. The integral from x naught equals 0 to c of gamma dx naught. Okay, so now gamma is a constant again, and because gamma is a constant, this integral just gives us rho v infinity gamma times c. Now we can look at the lift coefficient, the sectional lift coefficient, and that is defined as the lift over 1/2 rho v infinity squared times c. So if we just plug this solution in here, we've got rho v infinity gamma c over 1/2 rho v infinity squared c. So the c's cancel, the density cancels, one of the v infinities cancel, and so we're left with 2 gamma over v infinity. And that is equal to our lift coefficient, and so we can actually solve for gamma and say that gamma is equal to our lift coefficient times v infinity over 2. Okay, so instead of gamma in our equation here, we can actually just put in the desired lift coefficient that we're looking for with this delta pressure. So let's plug that in, and let's see. So I'm just going to move down here and say now dyc dx. We're just going to plug this in is alpha plus, instead of gamma, I'm going to do my lift coefficient, CL tilde. The v infinity is going to cancel, and I'm going to be left with a 4 pi in the denominator. And then that's multiplied by the natural log of c minus x over x. And we can actually rewrite this as alpha plus CL tilde over 4 pi times the natural log of c minus x minus the natural log of x. And that's helpful when we're ready to integrate, which is our next step here. So what we've solved for is the slope of the camber line. That's all thin airfoil theory cares about, is the slope as a function of x, so the change in camber line with respect to x. But we need to find the actual camber line, which is the integral. So yc, the actual camber line, is the integral of dyc dx times dx. So we actually need to integrate this equation here. And so when we do, what we'll get, so we're going to integrate this guy here, and we'll plug it in. So what we're going to get is alpha times x, when we integrate that first term, plus CL over 4 pi, and the integral of the natural log of some constant minus x is simply x minus c times the natural log of c minus x. There we go. And the integral of this guy here is x natural log of x minus x. And we've got a minus sign out in front of that. And so I'm just going to flip the signs on those. We're going to have a minus x natural log of x plus x here. Okay, so the x's cancel, so we can get rid of those two x's. And we'll just kind of clean this up here. So yc, oh, and we forgot our integration constant up here, plus c. So each of those integrals will have some constant. They're inside of this the parentheses here, but we can multiply them by some constant, and it's still just a constant of integration. So I'm just moving that outside for the time being. Okay, so so we can just kind of clean this up here. We've got alpha times x plus CL over 4 pi times x minus c natural log of c minus x minus x natural log x plus c. Okay, so that's our camber line. We have a couple things that are unknowns that we're going to solve for here in a minute, but first I'd like to rewrite this in non-dimensional form. So we have everything in terms of x's and c's, and I'd really like to write this whole thing in terms of x over c, so in percent chord. So in order to do that, we can divide this first term, or excuse me, we can divide through the right hand side, or the parentheses here, by c. And so I'm just going to pull a c out front. So we're going to have CL times c over 4 pi. And that will give us x over c minus 1 times the natural log of c minus x minus x over c times the natural log of x. Okay, so I just pulled a c out front there. And now, in order to get the x over c inside of the natural log, I actually have to do something. We have to use the rules of natural logs here. and I'm going to actually have to subtract I'm going to have to subtract a natural log of c inside of this term here. So what I'm going to do is minus x over c minus 1 times the natural log of c. So I'm going to have to subtract that off in order to be able to get that term there to have a c over c and an x over c. But because I'm subtracting it off, I'm going to actually have to also add an x over c minus 1 times the natural log of c. Okay, so for that first term, we're going to add and subtract this, which is just 0. And it just gives me a way to reorganize that. And then I'm going to do something similar here with the second term. I'm going to have to, we've got a minus x over c there, so I'm going to have to do a plus x over c times the natural log of c and minus x over c natural log of c in order to be able to get that into an x over c term. Okay, so let's see what we get once we plug all that in. So we're going to have y of c equals alpha times x plus CLC over 4 pi. And there's a couple steps in here. Well, we'll just work through it. So I'm for the first term, we're going to have x over c minus 1, and then I've got natural log of c minus x over c. Let me back up there. C minus x over c is just going to be 1 minus x over c. So that was a combination of this term and that term there. And then we're going to have a plus x over c minus 1 times the natural log of c. Okay, so that's that first term. And then for the second term, we're going to have a minus. I'm going to pull the minus out front here. We'll make these actually curly brackets. So I have a minus x over c natural log of x over c, and that takes care of this term and that term, and so then we're left with a plus x over c natural log of c. Okay, so I think we did that right. We've got our constant of integration out here, and we can keep simplifying this down here. So alpha x plus CLC over 4 pi. So this first term doesn't change, x over c minus 1 times natural log of 1 minus x over c. Now the second term here, I'm going to split up, and I'm going to have an x over c times the natural log of c. Minus natural log of c, and then we'll bring this negative through. Now we've got minus x over c natural log of x over c minus x over c natural log of c. All right, and then we've got our constant of integration out there. All right, so now we've got a plus x over c natural log of c and a minus x over c natural log of c, so those two will cancel. And then this minus natural log of c is actually just a constant again. So I'm going to bring that out and add it to my c out here. And so now we've got alpha x plus CLC over 4 pi times x over c minus 1 natural log of 1 minus x over c. And then all that's left in here is a minus x over c natural log of x over c plus a constant of integration. Okay, so we were able to go from this equation up here all the way down to this equation here and non-dimensionalize everything, all the x's. So we've got x over c's. Let me just make sure that that's correct, what we have here. Yeah, okay, I think we did that all right. Okay, so this is our camber line equation, but we have two unknowns here. We have this constant of integration that we don't know out here, and we also have this alpha term. So let's start with the constant of integration, the c at the end. So one thing we know is that we'd like our camber line to actually start and end at 0, right? So that's kind of the definition of the camber line. It's got to start at the leading edge and go to the trailing edge, and the y value at both of those locations is 0. So we know that y of c at 0 has to be equal to 0. So let's plug that into this equation. So for the first term, we're going to plug in 0 for all of the x's, okay? So this term is going to be 0 because we've got an x there. We go in here, x over c is, so this term is non-zero. When we plug this in, we get the natural log of 1, which is 0. So this term will disappear. And then over here, we've got an x over c, which is 0. And so that drops out. And then, so we're going to be left with this whole thing is equal to c. So that means that c equals 0. Okay, so now let's look at y of c at 1, or actually at c. At the chord, that's also got to be equal to 0. So let's walk back through this. So that first term is going to be, what we're going to get is alpha times c, a little c now. This is little c, our chord. And then we can keep walking through this. We've got x over c. When we plug in the c there, we're going to get a 1. Minus 1 is 0, so that term drops out. And then over here, when we plug in this x over c, when we put a c in there, we get natural log of 1, so that term drops out. So that's 0, and then c is 0. So, so we're left with alpha times little c is equal to 0, which means that alpha has to also be 0. Okay, so that was pretty simple, and what that gives us then is a yc, and I'm going to move this little c over to the left-hand side. So we've got yc over c is equal to CL over 4 pi times x over c minus 1 natural log of 1 minus x over c minus x over c natural log of x over c. And this is our camber line. This is our non-dimensional camber line. And again, this was the NACA 1 series camber line, the uniform load camber line. Now I've also seen this written with a negative out front, so I'm just going to write it that way as well. You can pull a minus out front, so we got CL over 4 pi. And for that minus, I'm just going to flip the direction of this first, the stuff in the first parentheses here. Natural log of 1 minus x over c. And then we have that minus out front, so that becomes a plus x over c natural log of x over c. So you might see it written this way, but anyway, both of these are the NACA 1 series camber line, and it comes from the uniform load camber line. So next we're going to look at some results from this and see what the pressure distributions look like.